So my name is Hervé Martin. I am professor of geology at Clermont-Ferrand University in France, and I work on the early Earth and mainly on the genesis of the early continental crust. So we'll speak about geology now. So life as we know it today on Earth requires at least some components, and these components are, of course, liquid water, carbon, so here is a diamond, and of course energy. So I don't know if I will have time to speak about everything, but we will start looking at the availability of liquid water on Earth. Before starting, I would like to put some temporal and geographic markers, some milestones. And of course the first one is the words that I will use, and we can divide the geological time in several periods that are Archean, Archean, Proterozoic, and here we do not see it, but Phanerozoic time. So, of course, the beginning is Earth's accretion. 4 billion years is the age of the oldest known rocks. The end of Archean, 2.5, is the beginning of what I would say modern Earth. So the Earth began to work. The dynamic of the world was more or less the same as today, at least not in detail, but at least in general. 0.5 is an explosion of, let us say, fossils. It is a Cambrian explosion. And of course, today is a lecture. So I will also speak about some places in the world where samples were taken. So the oldest one is from Jack Hills in Australia. These are not rocks, but crystals of zircon. So they are 4.35 gigayears old. We'll speak about Isuak gneisses here, more or less 3.8. Nuvvuagittuq gneisses, 3.75 here, and rocks from Australia and South Africa, 3.4 billion years old. So now have a look on the place where we can find these rocks. So Jack Hills is somewhere here in Ilgan Craton, here in southwest Australia. We have Isua in southwest Greenland, Barberton in South Africa, here near the boundary with Swaziland. Here we have Pilbara Craton in northwest Australia, and Nuvvuagittuq in Quebec in Canada here. So I will speak about these places, mainly about these places. Okay. Now, if we look here at the condition for habitability of planets, and here are telluric planets. Here is the distance to the Sun in astronomic units. Here is time. And of course, one of the conditions for habitability is the presence of liquid water at the surface of the Earth. And if we look at the habitable zone, so we have this in blue. So here is too close to the star, so too hot, and here is too cold for having liquid water at the surface of the planet. If we consider now greenhouse gas, the habitable zone could be greater. And fortunately, the good news is that we are on an habitable planet. So now, okay, this means that there is water at the surface, and the question is, when does water appear on the surface of the planet? So if we look at old supracrystal rocks are rocks emplaced at the surface of the Earth that can be sediments, but can be lava too. And here, for instance, we have lava with a pillow shape here. These are from Isua in Greenland. And this kind of shape is typical of emplacement in water. This can be an ocean, this can be a lake, but this is emplacement in water. So this means that at 3.8 in Greenland there was water. And we have also a lot of sedimentary rocks, just like here. You can see the banding here of the sedimentary rocks, or here too you have this banding of sedimentary rocks. In addition, maybe you have seen this paper, it was published in last August, And this is a paper from Nutman that describes in Ishua this kind of structure that he interpreted in terms of stromatolite, so in terms of traces of life. And okay, whatever it could be, this means that these rocks are emplaced in the water, Okay, so at 3.8, it's clear that there was a lot of water at the surface of the Earth. Now, if we try to go back in time, and if we look at zircon from Jack Hills, the problem in Jack Hills is that we only have minerals. The rocks have disappeared. Zircon is a mineral that is very resistant to weathering, to alteration, and it survives to these processes. But the other minerals that were in the rock, in the host rock for these zircons, have disappeared. So the only survivor are these zircon crystals. So now they are deposited in sediments, in young sediments, here. And here are the zircon crystals. And the age of these crystals are 4.35 million years. So some people report an age of 4.4 here, but as you can see, it is along a crack. Here there is a crack, some small fracture in the zircon, so maybe the age could have been modified. So 4.35 is admitted age for these zircons, and maybe could be 4.4. So these zircons, they crystallize in a magma. So they not crystallize alone in the magma, they crystallize together with other minerals. And during their growth, they incorporated some of the other minerals that were crystallizing together with them. And if we look at this, some of these crystals of zircon, they contain some small inclusions of other minerals. That can be quartz, as you can see here in red, but this can be plagioclase. Where is plagioclase? Somewhere here. And some mica, muscovite, biotite here, and so on. If we look at the composition of these minerals, and of course there is a problem. The problem is a problem of cracks and of small fractures in the minerals. Some people say, okay, if there are some small fracture in the minerals, some fluids, water or other hydrothermal fluids, could have modified the composition and allow the crystallization of some minerals. So this compilation of data is made far from the cracks, far from the fractures. So these minerals cannot be suspected to have been modified or generated by fluid circulation into the crystals. And so what we see here is that these rocks contain quartz here, K-feldspar, plagioclase, muscovite, biotite. That means that they contain quartz, feldspar, and mica. That means that the composition of the magma was a granitic composition. And so you know that granite is continental crust. So one of the what is said by these zircons is that they crystallize in very early continental crusts that appear very early in our planet history. Some zircons, the composition of zircon, I didn't spoke about this, but is silicate of zirconium, is ZrSiO4. But it can we can have some amounts of titanium introduced into the lattice of the crystals, and the amount of titanium is dependent on the temperature. And we have this kind of relationship. Here is the amount of titanium in zircon crystal, and here is the temperature. So we have this kind of relationship, and in other words, it's possible if we know the amount of titanium in zircon crystal, we can have an idea of its temperature of crystallization. And of course, looking at the early Earth, we expected very high temperature. And here we have the amount of crystals, here the temperature deduced from titanium content in the crystal, we can see that the temperature is low, at least for a magma. It's about 700 degrees, between 680 and 750 Celsius degree. So it's quite low for this kind of magma. If we look now here at the temperature and pressure diagram, we have here the dry solidus for granite. So that means that here everything is solid and melting begins at higher temperature here. Now if we look at hydrous solidus, that is melting in presence of water in the system, of course the temperature are lower. So here is dry melting, here is hydrous melting. And if now we look at the temperature of crystallization of the magma, the host magma for Jekyll's zircons, we can see that this is not consistent with dry melting, but this is consistent with hydrous melting, which means that there was water available in the system at that time. So this is the first important point. So water was available as early as 4.35 million years on Earth. Now if we look at another chemical characteristic of these minerals, we can look at the oxygen isotopes, the stable isotopes, and here is time, and here is the isotopic ratio, here is the mantle value, and the composition of the zircons is clearly above the mantle values here, and which is known, when we have this kind of value, this is known as a characteristic of low temperature hydrothermal alteration. So once more time, this kind of evidence indicate that there was water available and that the source rock from the granitic magma in which zircon crystallized interacted with low temperature water. Another system can be lithium here. And if we look at this isotopic system, we have here mantle value with some variation around these values. And here is the composition of Jekyll's zircons. So they cover a very large area between 8 and more or less minus 18. And we have very low values here. If now we look at Archean granite, typical Archean granite, we can see that the values are concentrated here, more or less consistent with mantle-like values here. Now, if we look not only at Archean rocks, but at continental rocks from different ages, we can see the same repartition around the mantle value here. Now, if we look at the same kind of rock, but strongly weathered, weathered by the action of rain and water and so on, we can see that you have a widespread distribution here with very low values. So it seems that these very low values that we have here are characteristic of the interaction of water with a rock, with the source of the granitic rock. So once more time, we have here an evidence for the presence of water during the genesis of these rocks. It seems that water was available on Earth very early, less than 200 million years after the beginning of accretion. So now we can try to look more carefully to the data. And if we look at the minerals in inclusion in the zircon crystals, we can see that we have quartz here, we have feldspar, as we have seen, and we have mica muscovite. And this kind of composition, quartz, feldspar, and muscovite, is typical of what we call paraluminous granite. So that the geologists call S-type granite. S is for sedimentary origin. So this kind of granite is generated by melting of clay or mica-bearing sediments. So what we can see here is that the source of this granite was some sediment, and sediment rich in clay minerals. Now, if we try to take this mineralogical evidence in pressure temperature diagram, we can see that the place where we can have quartz, plagioclase, biotite, muscovite, and K feldspar is this field here. And if we consider the silica content of the magma here, we have a field of pressure temperature that is around 700 degrees, which is consistent with the titanium data, and a pressure of 7 kilobar. So, okay, these are the conditions of genesis of this granite at low temperature. And this means that there were clay, so there was this kind of phyllosilicate minerals in the source of the granite. So clay minerals are typical because we have sheets like this, and they are foliated minerals. And some people consider that this kind of sheet minerals, here is a mica, could have acted as a template for the synthesis of organic molecules. So that means that this kind of sheet minerals were available on Earth very early in the history of the Earth. So I don't know if they really, because I'm not a biologist, so if they really play or not a role in the synthesis of organic molecules. But if they played, they could have played this role very early in the Earth's history. So here is some evolution of minerals on Earth in course of time. So here is time. Here is the amount of mineral species. This is from Hazen work. And he considers that, and we can see that before the accretions, we have only very few minerals, and these minerals were dry minerals, just like olivine, pyroxene, and so on. So minerals that do not contain water. And when water was available on the planet, of course, the amount of minerals increases significantly due to the interaction of water on dry minerals. And of course, after, when life became important on Earth, we had another increase on mineral number. So what is important here is that the action of water on dry minerals took place very early in the history of the Earth. So if this sheet mineral could have played a role in the apparition of life, or at least on prebiotic chemistry, this could have been very early in Earth's history. So, just an example of hydration of dry minerals is what is taking place today in ridge system. In ridge system, we have, of course, magma chamber, and this magma chamber give crystallization of this magma chamber give the oceanic crust with the pillow lava dike complex, and the minerals that form from this magma are mainly olivine, so no water, pyroxene, no water, and garnet, in the source at least, there is no water in this mineral. So the amount of water in the parental magma is very low. But of course, in the ridge system, there is a lot of fractures, a lot of faults here. So water is going down in the crust, and of course heated and returned to the surface, giving rise to this kind of white or black smokers. And of course water interacted with the minerals, with these dry minerals, and the resulting minerals are some kind of antigorite that contains a lot of water, talc with a lot of water, chlorite with water, amphibole with water. And the amount of water included in these minerals can be as high as 5%. So this is this kind of hydration of dry minerals into hydrous minerals. So, okay, the conclusion, I already gave it, but if we assume that the mica sheet can really act as template for synthesis of organic molecule, this could have taken place very early in the Earth's history. When we look at the Archean terrains, we can see a lot of scherts. So these scherts are silica deposits. So this silica is deposited in hydrothermal system. It can be deposited directly in the seawater, but it can also invade previous rocks and silicified these rocks. So here is a very famous chert in Australia, in the Pilbara Craton, is a marble bar here. And Okay, here is a look on these rocks, which are made mainly with silica. So, some geochemists try to discuss some characteristic of water, considering that these rocks formed by precipitation of silica in water, and they use some system, for instance, a stable isotope of oxygen, in order to have an idea of the temperature of crystallization, because the fractionation of these isotopes is can be temperature dependent. And of course, what we see here for, this one is silica, sorry. Can use also silica isotopes, and this silica isotope gives temperature of about 60 to 80 degrees for seawater temperature at 3.8 million years. If we look now at oxygen isotope, we can have more or less the same result. So, looking at this data, we can conclude that seawater was very warm at this time, because today it is between, let us say, 10 and maximum 20 something. So, the conclusion is during Archean, in early Archean, the temperature of water was very high. Unfortunately, other people, Jeffreys here, 10 years ago, based on other assumptions on fractionation of oxygen isotope, reached the conclusion that the temperature was only around 30 degrees. So there is a disagreement between the two approaches. More recently, there was a discussion by one researcher, is Marin Carbone, and she considers that we have two kinds of cherts. Some cherts are sedimentary rocks, so they chemically precipitated directly from seawater. And in this condition, the isotopic signature is that of the seawater. And other cherts result from hydrothermal replacement of precursor rocks. That means that a rock is invaded and silicified by these hydrothermal fluids. And the isotopic signature is the isotopic signature of water, but also of the previous rock. So there is addition of two signatures. So she proposed some criterion in order to distinguish between these two kinds of rocks. So I will not detail this. But when we consider only the sea cherts, that means the chert that precipitate, that are supposed to have precipitated directly from seawater, we have a temperature range from between 37 and 52 degrees. So this is not 70 degrees, but this is quite warm too. So it seems that at the end of the Archean, the seawater was warmer than today. But one question remains, is that, of course, cherts form in hydrothermal system. So the question is the temperature that we obtain, is it the temperature of the whole ocean or only the temperature around hydrothermal system? So this is the question. And of course we have until now we have no answer to this question. Another approach about ocean water consists in looking at fluid inclusions trapped in minerals. So this one is not seawater, but this one shows what is a fluid inclusion. Here are quartz crystal, and we have liquid inclusion into this crystal. So during their growth, the crystal have some defaults, and there are some holes, and these holes can be filled by magma, if the crystal crystallized in a magma, or by fluid, if it is formed in, for instance, in seawater. So sedimentary minerals could have trapped some water here in this fluid inclusion. And in this condition, if we know the composition of this fluid inclusion, we can have an idea of the composition of the seawater at the time when the mineral crystallized. So here are some fluid inclusions in minerals. And I like this one. This one is from an emerald from Minas Gerais in Brazil. And we have the fluid inclusion here. And it contains a crystal of halite, that is salt. We have vapor and water or salted water here. So if we analyze this kind of inclusion, we can have an idea of the composition of the seawater. And here is an estimation of the composition of seawater in course of time from ADN here to present day here. And we can see very big changes, for instance, for sulfur here, and here for iron, and this takes place mainly at the Archean Proterozoic boundary, and later, but we'll not discuss this. Karim will discuss this afternoon. So now we can try to look at the same thing in this kind of diagram. So we have some ions that are dissolved in water, and the concentration in fluid inclusion is divided by the composition, the concentration in present-day seawater. So present-day seawater have this flat line. The value is 1, of course. And if we look at the Archean curve, we can have this kind of curve. So there are some strong differences and some similarities. If we look at, for instance, chlorine, bromine, sodium, potassium, magnesium, we have more or less the same values as today. Maybe the concentration is slightly higher. Some people say twice higher. But we have big differences for other elements, just like SO4, iron 2, calcium, and strontium. So now if we look at sulfur here, sulfate, today the SO4 ion in water is result from this reaction, is the action of oxygen, atmospheric oxygen, on sulfur, just like sulfide, just like marcasite or pyrite and so on. So here we can see alteration of marcasite crystals. Marcasite is sulfide FeS2 here. And of course, this reaction provides SO4 ion that go dissolved in water and go to the ocean. But during the Archean, there was no oxygen in the atmosphere. So this reaction was not taking place during Archean time. So the sulfur was not altered by oxygen. So the SO4 ion doesn't go to the ocean. So this accounts for the depletion of this ion in the ocean, in the Archean ocean. So, okay, there was a depletion, but we can explain this by the absence of oxygen in the atmosphere. Similarly, we have very high contents in iron 2 in seawater. And you know that the reduced iron 2, is soluble in water, while the oxidized iron is not soluble, is insoluble in water. And we can see this, for instance, in tropical area where this iron remain in the soil after alteration, for instance, of granite. The iron remain and gives this red color to the soil or to the rocks in these countries. This means that iron is not mobile today. But during the Archean, there was no oxygen. So the iron was not on this oxidized form, but was reduced iron. So it was soluble in water and moved with the river, moved to the ocean. So it accumulated in the ocean. So this accounts for the very high content in iron in the Archean ocean. So now if we look at what we can assume to have been the CO2, the carbon dioxide content in the atmosphere in course of time, we have this kind of curve. So CO2 was abundant in the early Archean, and the contents of CO2 decreased because it was used to form carbonate, and the carbonate were reintroduced into the mantle, so extracted from the atmosphere. But the important point is that we can calculate the pH of seawater in equilibrium with this kind of CO2-bearing atmosphere. And the result is this kind of value. So that means that during the Archean, the pH of seawater should have been lower than today. That means that if now we look at this calcium and strontium content, as the pH was lower, of course, the calcium and the strontium precipitated less easily as today, so their content in Archean water were higher than today.
What do you think the anion was that could compensate for such a large amount of iron?
Sorry?
What do you think the anion, the negatively charged ion, was that could compensate for iron 2? It's huge.
Yeah, it's very, very huge content, yeah. This is the result of some measurements. There is a discussion about the representativity of these fluids, because they can be also formed in some kind of evaporitic environment and doesn't represent the real, the whole ocean. So there is a discussion about this, about the representativity of fluid inclusion in these minerals. Well, okay. We have already seen these picture, and just to say that continental crust existed during the early Archean. But one of the questions, and a very important question, is the question of emerged continent. So this is not because we have continental crust that we have emerged continent. And this point of emerged continent is important. So today, if we look at the cumulative percentage of emerged continent on Earth, we have this kind of curve. And if we put here, of course, the level 0, the sea level, we can see that we have more or less 29% of emerged continent. During the Archean, many people consider that the thickness of oceanic crust was not the same as today. It was thicker for many reasons, because of a higher geothermal gradient and so on. And that the level of water was slightly higher. So they proposed this kind of curve for Archean crust, this kind of distribution. And it seems that, of course, as we can see here, the amount of emerged continent during the Archean was lower than today, and the maximum value is 12%, and probably slightly less. So during the Archean, the amount and the proportion of emerged continent was less than today. So this is something quite important. So here, but we have evidence that we had this kind of emerged continent. For instance, in some places, just like here in a Barberton belt at 3.4 billion years, we have some mud cracks of some fossils mud cracks. So here is a present-day mud cracks. This is what happens to mud when we dry this mud. We have these cracks that appear, and of course, this can be produced only if water evaporated. So if there was some emerged part of the continent. And so this is a proof for that. We have also some gypsum and some evaporite minerals. Here this is in Pilbara. And this is also an evidence for emerged continent. But we have evidence for that, but this was only a small proportion of the surface of the Earth that was emerged during this period. Of course, continents are generally made of continental crust, but we have some places on Earth today that are emerged, just like Iceland, which is not continental crust, but this is oceanic crust or oceanic plateau. So, okay, we have also, Hawaii Island or La Réunion Island that are emerged, but this is not continental crust. So we have to distinguish between the nature of the material, is it continental or oceanic, and the possibility to have emerged lands. So why are we discussing this? I am discussing this because if we look here at the amount of nutriments in seawater today, we can see that this amount, of course, of nutriment, the maximum is red, the minimum is blue or violet here. We can see that the maximum is along the coast, along the continents. So that means that a lot of nutriments are coming to the sea from the continents. So the presence of continent can be very important for maybe the appearance of life, but at least for the development of life, this could be very important. And during the Archean, if we follow the models that I showed you before, the amount of continent was by far less than it is today. Another point that I want to discuss here is the role of tides. These are sediments. So some sandstones from Barberton in South Africa. And you can see here there is some stratification that are some cross bedding and so on. And if we look here, they are very well preserved for very old sediments. And we can see here some figure that the geologists interpreted are due to tide current. So, with some cycle from day cycle and some cycle from months. And here is a modern equivalent. So we have some rhythmicity in the sediments. So here is a rhythm for 1 day, and here is for 1 month. So if we look at the rhythmicity in the sediment, we can have an idea of the motion of water and about the tides. And this is what happened here, looking at these sediments in South Africa. Sedimentologists report the frequency here, and they can show that there was a period of this period as interpreted in terms of tides, and they show that the anomalistic months was about 20 days, when today it is 28 something, I don't remember exactly. And that at that period, the length of a day was only 11 something hours. So the tides were more frequent than they are today. Similarly, other people work, for instance, on this kind of a coral. This is a coral, and they show some rhythmicity here. And the rhythmicity in the growth of the coral is also interpreted in terms of cyclicity between day and night. And they show, for instance, that this kind of fossil emplaced about 400 million years ago was consistent with days that of more or less 22 hours. So that means that when we go into the past, the days were shorter than today, and this is due to the fact that the moon is going progressively away from the Earth, and this makes the rotation of the Earth becoming more slow. So the motion of the Earth is slower and slower. So if we put this kind of data in a time diagram, here is the length of a day, we can see here the data for quite recent period, so it's mainly made on fossil, as you can see, this kind of brachiopods, stromatolite, corals, and so on. And here is on the rocks of South Africa, so we have a line like this. But, of course, there is an uncertainty because you have also points here. But what is very clear is that at that period, the moon was closer to the Earth and the days were shorter. So that means that during Archean and Hadean, the moon was closer to the Earth. So the effect of the moon on Earth was greater, and the range for tides was greater than today. And that means that the tides and the seawater was able to go far or farther than today inland. And some people, I'm not sure that this is a good values, but some people, and this is an extreme proposition, consider that the tides were more or less 100 meters high at that time and could reach more or less 100 kilometers inland. So that means very big tides, and the effect of the tide, of course, will be to, as I say somewhere here, to flood the continent, sometimes to dry it very soon after, and of course will give a very strong erosion. And erosion is also a way to bring nutriment from the continent to the ocean. So maybe that was more efficient than today. So another point is that some people propose models for prebiotic chemistry. And for instance, this is an old model by Comeras et al. And he proposed that in order to synthesize some peptide, we need some alternation of dry phases and aqueous phases. So very rapid change in dry and aqueous. So this kind of situation, if this is true, I don't know, but if this is true, of course, this means that the important tides and with a very rapid rhythm for tides was very favorable for this kind of chemistry. So this, on early Earth, the fact that the tides were important and happened more rapidly is a parameter that is consistent, that could be consistent with this. Maybe you have seen this paper by Lath, and also his conclusion is that some selection and some amplification of DNA molecule is favored by tidal flooding and by the fact that we have a very important tide. Similarly, another paper, not very old, considers that in order to practice, to have efficient and prebiotic chemistry and to extend to some molecule, it's necessary to have this kind of motion in mica sheets, and this kind of motion can be related to drying and to dry and aqueous phases. So if we have a fluid flow, important fluid flow, maybe daily flow like this could have some influence. So I do not know about prebiotic chemistry. I'm not biologist or chemist. But what I would like to say is that some models consider that the alternation of dry and hydrous period could have played an important role in prebiotic chemistry. And what I say here is that during the Archean and Hadean, the conditions were favorable to this kind of assumption because tides were important and occur more often than today. Another important point for life, for its apparition on Earth, is the role that could have played the magnetic field. The magnetic field, of course, will prevent the erosion of the atmosphere by the solar wind. You know that this is probably what happened on Mars. The atmosphere disappeared when the magnetic field stopped. And of course, the radiation coming from the solar wind, from the sun, and that reached the surface of the Earth could have destroyed the life because they have a lethal effect on living beings. So, another important parameter for the life is the existence or not of this magnetic field. And the question is, when did this magnetic field appear on Earth? So you know that Earth is made of several shells. The first one is a solid core that is made of iron, and maybe some small amounts of nickels, but mainly iron. So surrounded by a liquid core. So this one is solid and this one is liquid, more or less the same composition. So there is a solid mantle made up of silicates. Here is mainly olivine and pyroxene, and some crust at the periphery. So one of the questions is when this kind of differentiation took place. When does iron separated from silicates to form core and mantle around it? This is important because convection in the outer core, that means in the liquid part of the core, is what gave rise to the magnetic field. So the problem of apparition or formation of the core is important because this is a prerequisite for magnetic field apparition on Earth. So there are some methods that allow to date the apparition of the magnetic field. And this is based on one extinct radioactivity. This is radioactivity, this is a decay of Hafnium-182 in tungsten-182. And the half-life is very short, 9 million years. And you can see here is the curve of abundance of hafnium-182. And you can see, looking at this curve, that at about here 60 million years, there is no more hafnium in the system. So this, we can use this kind of technique only for dating events that took place very early, less than 60 million years after the beginning of accretion of the Earth. So here is the equation. And in addition to be an excellent system for dating very early events, we have hafnium that behaves as what we call a lithophile behavior. That means that it is incorporated in silicate. So, in other words, hafnium will go in the silicate in the mantle. And when it decays into tungsten, tungsten is siderophile and will go into the core. So this system is excellent for dating very early events, but also for looking at the separation between silicate and metal. So let us imagine that core differentiation took place after 60 billion years. So, of course, at that time, there is no more hafnium-182. It is totally decayed into tungsten. And, of course, the whole tungsten will be incorporated in the core, in the metal in the core. So this is not very interesting for us. But let us now imagine a more favorable situation, and that the core differentiation took place before 60 million years. In this case, one part of hafnium-182 is transformed into tungsten and will go into metal. But one part of hafnium-82 remains, so it is incorporated in silicate, and incorporated in silicate, it will decay into tungsten. So, in other words, in order to be very simple, if we found some tungsten-182 into the silicate, that means that this event took place before 60 million years. If not, all the tungsten-182 will be here in the core. Of course, if I talk about this, this is because we have some excess of tungsten in silicate, in the mantle. This means that the differentiation took place less than 600 million years after the nucleosynthesis of hafnium-182. We can have more precise results. So here we have plotted ratio of tungsten isotopes against time. So there is a big gap here. And here is the curve of chondrite value of a chondritic reservoir is for these isotopes. So the curve is something like that. And if there was no iron silicate differentiation on Earth, we should have this value on Earth today. And in fact, we have this value in the mantle. So we have an excess of tungsten. And making some assumption, we can construct this curve and see that the differentiation could have taken place at 30 million years. So this is one of the value we can conclude from this. This is that the core differentiation, the differentiation between the core and the mantle, took place very early, 30 million years after the hafnium-182 nucleosynthesis. Okay, this is ideal situation. This ideal situation is that we took into account only this reaction. That means that the whole tungsten-182 is coming from decay of hafnium-182. In fact, on the moon, some people show that we can have 182 tungsten by interaction between a neutron and tantalum-181. So that means that the whole, we can have cosmogenic 182 tungsten. So the whole tungsten is not coming from the decay, in this case, is not coming from the decay of hafnium, but can have another origin. So this can modify slightly the value that we obtain. Another assumption is that we made for this calculation is that this ratio, 182 hafnium, divided by 180 hafnium, is constant in the whole solar system. Well, this is quite realistic, but we have no evidence that this is the case. And if this ratio is not the same everywhere in the solar system, the value should be slightly different. Okay, these differences, even if we take this into account, are not very, very big. And one thing that is clear is that the differentiation of core and mantle took place very early in Earth. Maybe not 30, but more or less certainly less than 60 million years after nuclear synthesis of this hafnium isotope. So the question is, okay, we have a core, we have the mantle, but this doesn't mean that we have a magnetic field. This is, of course, this is something necessary to have a metallic core in order to have magnetic field, but magnetic field could have started later. So if we look now, here is time again, and if we look here at the strength of magnetic field, we have this kind of curve. Here we have values up to 3.6 billion years. More recently, 2 years ago, some people work on Jekyll circles, and they can add some points here. And okay, we have evidence for apparition of the magnetic field quite early, at least at 4.2. But the problem is that, as you know, on Earth we have no material older than these zircons. So we cannot have evidence for magnetic field before here this is 4.2 billion years. Maybe we can have a look on Mars. And Mars, you know, we have very old terrains here with a lot of impact crater, and here more recent terrains, and with the volcanoes here more recent. And if we look at the map of magnetic or remnant magnetic field on Mars, we can see that it appears only on very old terrains, older than 4.3 million years. So that means that on Mars, the magnetic field appeared also very early in the history of the planet. So okay, we cannot go further because we have no very old materials that could have recorded this magnetic field. But on Earth, at least at 4.2, the magnetic field was in place. So that means that the condition for prebiotic chemistry and maybe life appear very early on Earth. There was water. The water was not was warm. We had tides. There were sheet minerals and so on. So the condition for and the magnetic field. So the condition for life were present on Earth very early. We can look at the other important point is the presence of carbon. So carbon, of course, here is a pure carbon, it's diamond, and progressively we can make more and more complex molecule like this. And one thing that is quite surprising, at least for me, is that carbon is very abundant everywhere in the universe. So, for instance, in some meteorite here, we already have some amino acid molecule in this meteorite. In comet, there is a lot, just like Shuri here, there is a lot of complex carbon molecule, and as far as I know, recently, in last year, some amino acid glycine was discovered in Shuri. So that means that there are complex molecules in comets. And even here, if we look at the Orion molecular cloud, there is a lot of complex molecule in this cloud. So it seems that carbon is present everywhere in the solar system and in the universe. So what about carbon on Earth, and what about old carbon on Earth? There are many places where people discover very old carbon minerals, just like graphite. So one of the first places is Isua in Greenland, here. You have here helicopters that gives a scale for the picture. And there is a lot of sediment, just like this one, with levels of graphite. So in these sediments, we have levels with the graphite here, the black level. So this is graphite. Near Isua in Aquilia, there are some banded iron formation here, and in this banded iron formation, the banded iron formation is iron and silica. And in quartz crystal, for instance, there are some graphite. There is graphite here. Similarly, in Jekyll zircon, there are some inclusions of graphite. And maybe, I don't know if you have seen this, this was published last week. This is from Nuvagittuk, and Dodd reported graphite in some kind of tubes here in Nuvagittuk supracrystal in some chert, hematite-rich chert. So the question was about this carbon, is it consistent with life, or is it only pure, I wouldn't say artifact, but made without the help of any living being? So if we look here at the isotopic composition of carbon, here is time. So we have here the range of composition of schist from Isua. Here is a Nuvagittuk chert. Here are the sediments from Isua, the chert from Isua and Aquilia, here. And here is the carbon from Jekyll zircon. So everything here is graphite, but in different environments and at different ages. So, okay, if we look at the composition here of inorganic components, just like ocean, atmosphere, rocks, magmatic rocks, sedimentary rocks, the range of composition is somewhere here. If we look now at the degree of fractionation of carbon in organic matter, in living beings, just like bacteria and so on, the range is very wide, and we have this kind of range. So that means that if we look at the blue field here, if you look at this blue field, this could be attributed, these very low values can be attributed to life, because inorganic carbon is restricted to these high values here. So this blue field could be attributed to life. So that means that all this graphite could have been formed by living beings, by bacteria and something like that. This is true, but there is one point, is that the effect of temperature and the effect of metamorphism can change the degree of fractionation of carbon. And if we look at the composition of metamorphic rocks, that means rocks that were transformed by high temperature and high pressure, the range of fractionation of carbon is this. So that means that these values can be biological, but can be also due to metamorphism. And unfortunately, all these rocks, Nuvagittuk, schist from Isua, and Aquilia, and of course Jekyll zircon, were subjected to very strong metamorphism, to very high temperature. So, okay, this could be biological, but this could be totally abiotic. So we have in fact, we have no answer for this very early, very old carbon on Earth. Okay, just the last slides about energy. So on Earth we have two sources for energy. One, of course, is external. This is the sun, and one is internal. This is the heat from the internal part of the Earth. So the heat flux is very high for the energy coming from the sun, and very low, if by comparison, with what is coming from the sun. I say that this is very low, but this is enough for earthquake, for plate tectonics, and for volcanism, and so on. So this is relatively low. The mode of propagation is radiation, and here this is conduction or convection. So this radiation can be transmitted only in transparent media, just like air or atmosphere or water, more or less, and this only in solid. So that means that about, if we consider the dynamics of the Earth, of the internal Earth, the Sun has no effect on these dynamics because the Earth is not transparent, the rocks are not transparent. So that means that the control of volcanism, earthquake, and let us say plate tectonics is only due to internal heat. So we'll try to compare these two sources of energy. And first, if we look at internal energy, we have evidence that on the early Earth, the temperature or the amount of energy, of internal energy, was greater than today. If we look at this kind of rocks, which are comatiites, which are ultramafic lava and placed only during the Archean, we can have an idea for lava of the temperature of this lava looking at magnesium content in this lava. And if we look at this in a magnesium against the age, we can deduce the temperature here and see that during the Archean time, the temperature of emplacement of lava was greater than today. Today, the maximum in which system the temperature is 1,250, while in hotspot today is between 1,350 and 1,450, while during the Archean that was up to 1,700. So obviously, the temperature of lava emitted during Archean was significantly higher. So that means that the early Earth and the Archean Earth was warmer, at least internal Earth was warmer than today. Okay, so the origin of this energy, I suppose you already know it, so I will go rapidly. Today, this is of course, mainly due to the decay of radioactive isotopes. That means uranium, thorium, potassium, mainly these three elements. One part is the residual accretion heat. This accretion heat is the affects the transformation of cinetic energy of planetesimal into heat. So one part, one small part remains. One part is a latent heat of crystallization of the liquid core, and a very small part is due to terrestrial tides. You know, tides affect ocean, affect water in the ocean, but can also affect the solid Earth. And this, the motion of this solid Earth, of continent, for instance, induce production of heat here. You can see that all these sources were more or less given or appeared on the Earth at the beginning, and since this period they progressively disappear. The amount of radioactive element progressively decreases in course of time. The residual accretion heat was provided to Earth at the beginning, and progressively it decreases. For this is more or less constant, and as the moon is going farther and farther from the Earth, of course the effect is of tides is also lower. So in other words, the Earth progressively cools, or the amount of internal energy decreases in course of time. And for instance, we have here a curve that shows the internal energy and the decrease of this internal energy in course of time. And we can see, for instance, that 4 billion years ago, the amount of heat of energy was 4 times the amount today here. So the internal Earth was warmer. And we know that this heat was removed from the Earth, because if this heat accumulated, the temperature would have increased, and we should have a melting of the mantle of the crust and so on. So, and we didn't add this. So this heat was evacuated. And if we look at evacuation of heat today, here is a flux, the heat flux at the surface of the Earth, and we can see that most of the heat is evacuated by mid-ocean ridge system here. So the internal heat today is evacuated by the mid-ocean ridges. And there are two ways for evacuating this temperature: volcanism here, and of course hydrothermalism. Hydrothermalism is linked to volcanism, but this is another process. Volcanism, you transfer the magma to the surface, and here you heat, your water penetrate into the crust, is heated and go out. So that means that as the internal heat is evacuated by a ridge system, we should have had more volcanism at ridge and also more hydrothermalism. And this is something very surprising. When you look at Archean terrains, there is a lot of chert, so that means a lot of hydrothermal derived rocks. And here, this is Barberton, and the whole hill or the whole mountain here is made of chert. This is a huge amount of chert, and when you look at Archean terrains, the amount of chert is by far more important than today. So this is consistent with a greater length, for instance, of ridges. This is important because, of course, if we look today on ridge, we have this kind of system which are in favor of chemiotrophic life. That means life which is not dependent from sun, which is only dependent on the energy coming from the internal Earth. So that means that during the Archean, I do not say that the whole life was like this, but this kind of environment was favorable for this kind of life. Now if we look at the sun, we have something quite different. Here is a time, and here is the luminosity of the sun. And what we can see here is that the luminosity of the sun in the Hadean was by far lower, so it was 30% lower than it is today. So the sun was, let us say, cold compared with the sun today. And progressively, the sun provided more and more energy that reached the surface of the Earth. So if now we consider, here is the temperature, if we consider here important value, that is 0 degrees Celsius, we can see that if we would not have atmosphere on Earth, the temperature would have been very low, but would still be very low at the surface of the Earth. Now, with our atmosphere, with the same atmosphere as today, today we have this kind of temperature of 15 degrees more or less as an average, and during the Hadean and Archean, the temperature would have been below 0 degrees. So that means that with the same atmosphere as today, the temperature of the Earth would have been under or below 0 degrees. So that means that we should have ice, frozen ocean, and maybe a snowball Earth. And in fact, when we look at the rocks during Archean times and early Proterozoic, we do not see this kind of rock, which are typical of, these are diamictite, this is not the good one, this is diamictite, and which is typical of glacier activity with this kind of very big blocks and so on. We do not see this kind of striated rocks here, typical of the action of ice on rocks and here on pebbles. So there is not at all evidence of snowball Earth, of generalized glaciation during Archean times. And we also have other evidences. We have seen that the temperature of seawater was between 30 and 50 degrees. So that means this is not consistent with the snowball Earth and with the frozen ocean and so on. So obviously the temperature on Earth's surface was higher than 0 degrees. So that means that the composition of the atmosphere was not the same as it is today. And certainly there were more greenhouse effect gases in the atmosphere, probably carbon dioxide and maybe methane, in order to maintain the temperature higher than 0 degree. Okay, this is the same here. And of course, the sun and the sunlight is, of course, necessary for photosynthetic beings, just like this kind of cyanobacteria and so on. So, we have, in fact, two sources of energy on Earth. One is the internal energy that creates the hydrothermalism and so on, which is more favorable for chemiotropic life, while the other source of energy is more favorable for phototropic life. And now if we compare the evolution of these sources, we can see two divergent evolutions. The luminosity of the sun increased during the history of the Earth, while the internal energy decreased. So this source of energy that is more favorable for phototropic life become more and more important in the course of time, while this one that is more favorable for chemiotropic life decreased in course of time. So I finished.